Last time you saw the definition of entanglement and how we write down the state of two qubits if we're given the state of them separately. So that looked like if I have two qubits and I know the state of the first one and I know the state of the second one, then I have this object here, which really is shorthand notation for this tensor product. What if I apply a unitary to the first qubit? Say I did that beforehand. So the first qubit has had a unitary, say U0, applied to it, and now I want to know the state of the two qubits separately. So I might say something like that. So I have U0 acting on side 0, nothing happening on side 1, and that looks like U0 acting on side. Okay, this kind of looks like there's a problem because I have a 4 by 1 column vector, and here I have a 2 by 2 matrix. So how is it that those things line up? And they don't, because this is not meant to represent a multiplication in linear algebra as written literally. So again, we have this shorthand notation, and it has to be understood from context that what we really mean is this matrix here. And the tensor product of two matrices looks the same as the tensor product of vectors, and we can write that out, but I won't write down all of the components. There's 4 for the first one, 4 for the second one, so there have to be 16, which is a pain. So let's just write down kind of the framework for it. So I have, let's give these some names just to be clear. Suppose I have A tensor B. Then that's the A00, so the upper left entry of A times the whole B matrix. And then the upper right element of A times the whole B matrix. And just for consistency and completeness, so they're both going to be repeated because the A matrix gets multiplied inside of the 2 by 2 matrix. So each element in A gets repeated 4 times, and then each element in B obviously gets repeated 4 times. So it's the same as when we had the tensor product of vectors. Okay, so that's just an aside. So let's continue. So we had this matrix here. That is what we mean when we have just one unitary acting on side. So if we expand left-hand side out, we have U acting on side 0, tensor identity acting on side 1. That is what we must understand if we know the thing in front of a 4-dimensional object is only acting on one of the qubits. And again, it needs to be implicit and understood which one of them they're acting on. Now we can look at more than just unitaries. We can look at projectors as well. So we can say, if I have 2 qubits and I'm only looking at a basis for the first, then I can always append an identity. So it's a nice trick, and a rule is, I guess, coming from what's written above, is if you want to make things explicit and it's not, things aren't written in such a way that you can literally interpret them, then what's missing is some identities. So you always stick in identities until the number of dimensions line up. So this here can represent this kind of scenario. I measure psi 0, sorry, but I don't do anything down in psi 1. So up here, one of two things could happen. Remember, I end up with this 0 or the 1 state, but what happens down here? And I guess more to the point, what would happen if instead of them completely separate, I actually had perhaps one of these entangled states, so arbitrary. In the original case, I would have just ended up with psi 1 on the bottom because I did nothing to it. I completely ignored it. Now I have an entangled state, potentially entangled state, or just have an arbitrary state. So remember, that looks like, use gammas, 0, 1, 0, 1, plus gamma 1, 0, 1, 0, gamma 1, 1, 1, 1. Now let's use the rule for measurement as before, and the way that we've defined how we're going to multiply matrices when only one of them is acting. So the probability with which I observe 0 given psi is the inner product of psi times this projector. So the projector is 0 tensor 1. And remember, you might see that as where if I take this literally, it doesn't make sense, because remember, this is on dimension 4, this is on dimension 4, and these things are on dimension 2. So I can't literally interpret that. I need to have known that that tensor identity was there. So in this case, we can look at this half of the computation, linear algebra, so I can apply that matrix to that vector first. So let's do that. And we see what happens is I have a 0, should we do it? Yeah, let's do it explicit, just to be clear. So I have 0, 0, tensor identity, and that acts on gamma 0, 0, 0, 0, gamma 0, 1, 0, 1, plus gamma 1, 0, 1, 0, plus gamma 1, 1, 1, 1. Now I need to put this green thing in front of every single one of these components. And so I have gamma 0, 0. And I'm going to, for the first one, let's do it for the first one, and then we can see how we can apply our shorthand notation to the other ones. So we have gamma 0, 0, that is just a constant, it comes outside, just sitting along for the ride. And we have 0, 0, and it acts on 0. Then we have this tensor. then we have identity, which acts on the other half. Right? Remember that shorthand notation for 0 tends to 0. So this is the first term. So term number 1 is equal to this. And we can do quite a bit of simplification here. So we end up with, in fact, the exact same thing. So the 0 and the 0 are 1. Identity times 0 is obviously 0. And so I end up with this 0 here, the coefficient, and then this new 0 here. So that's 0, 0. Okay? So applying this object, this matrix, to the first term actually hasn't changed anything. And we can see that the second one doesn't change anything either. So the second term is going to be left the same. So we have gamma 0, 0 plus gamma 0, 1. And the third and the fourth term will actually cancel. So, or not cancel each other, but get eliminated by this outer product, which is a projector onto 0, and we can see that the first qubit in each of these is in the 1 state. So when that 0 comes in and hits that 1 state, those are orthogonal, and so they go away. So this is, remember, that original question, the probability of, oh, no, not quite. That was just the what's in the screen here. And so now we have to take the bra of the original vector and apply this inner product with this reduced state that we've derived for the multiplication of the projector onto the vector. And we would see that a similar thing happens. Now we're multiplying, we're taking the inner product of two things that are written in the same basis, and either the terms will be the same, in which case the inner product will be 1, or they'll be orthogonal, in which case the inner product will be 0. So we can see that we're only going to pick up the first two terms because the second two terms are orthogonal to both of the first two terms which are left. So the probability of 0 given psi is going to be the magnitude squared of these. So when I multiply this again by what's left over here, so I'm going to do this in a product, and I'm going to pick up another gamma 0, 0 complex conjugate and gamma 0, 1 complex conjugate. So I get the magnitude. Okay, and one of the reasons we did this original multiplication on the inside first was not only because it simplified this calculation, but also remember the collapse rule, which said that we're going to project onto that observed state. That's the calculation we just did, divided by the square root of this probability. Alright. So this thing becomes gamma 0, 0, 0, 0 plus gamma 0, 1, 0, 1 divided by the modulus squared of those two things. And that also we could have just guessed or derived because the thing on the top might not have been normalized. Remember, the sum of the modulus of all of these terms added up equals 1. So the sum of two of them might not equal 1. that means we have to normalize what's been left after the projection. And so the state of the 2 qubits becomes this state here. And that you can also view as, by factoring out this 0 in the tensor product, you can also view it as so 0, 0, 0, 1 squared, 0, 1 squared. Okay, so this is the state of the first qubit, which makes sense because we measured just that qubit and observed 0. And the state of the second qubit is left in, well, what's consistent with seeing 0 from the original vector. Okay, so that's the general calculation. Probably one of the longer ones that you might have to do if you're looking at using these tensor products Dirac notation for 2 qubits.